And time to move on to the final talk of the session. It's an online talk by Amandeep Kaur, who's going to be telling us about modeling of surface gravity wave interaction with elastic structure in the presence of an arbitrary bottom. So, yeah, over to you, Amandeep.
Yeah. So, thank you, Professor, for a nice introduction. As my screen is visible.
Yes,
Thank you. Thank you. Myself, Dr. Amandeep. I'm working as assistant professor at Amity University in India. So the topic of my presentation is modeling of surface gravity waves interaction with elastic structures in the presence of arbitrary bottom topography. So now let me give you a brief introduction about the application of surface waves. Then I discuss the research problem, and then I will discuss the few of the results that is obtained, and followed by the conclusion and references. So the waves that are the disturbance that carries energy from one place to another place, it will not carry the matter with it. You can see these are the examples. Like in these pictures, the disturbance are generated by the fisherman by his boat, and the waves are generated. So now, if you talk about the application point of view, we have seen many very large floating structure which are constructed near the coastline. So, for example, this is the floating bridge. This is very large floating structure which is constructed near the coastline for the purpose of the land scarcity problem. And this is the another example which is constructed near the coastline, which is the rigid structure floating dock, which is used for the purpose of loading, unloading cargoes, passenger. So these are the very large floating structures. So these structure has a very scientific importance for their impact on the coastal areas. So now if we model these mathematical problem, we want to see the effects, then we can model as a flow problem. You can see this is the simple water channel problem, where the fluid is coming from, the water is coming from very far distance, and we have a few assumptions that is fluid is incompressible, inviscous, and irrotational. So the Guarding equation is the Laplace equation, and the free surface is given by y equals to eta, and the rigid bottom y equals to h. And we have a dynamic and kinematic free surface condition on this free surface, and this is the linearized boundary condition on the free surface. And we have another condition which is no slip condition on the bottom, which is del phi by del y, no slip boundary condition. Now if we see, we have a, this is the channel problem where we have a Guarding equation as well as the boundary conditions. Now, if we assume that the wave which is simple harmonic in time t propagating with angular frequency omega, then the velocity potential look like this. And the solution of this boundary value problem is wave-like solution, which is given by this expression. Now, this is nothing but this is the eigenfunction, and this k naught is the eigenvalue which generally satisfy this dispersion relation on this free surface. Now, if we talk about the scattering phenomena, that if there is some object in the path of the incident wave, then some part of the wave will be reflected back and some part of the wave will be transmitted throughout the gap. But in nature, we have seen this, the bottom topography is not flat bottom, it may be any kind of undulating bottom. So which is given by this y equals to h of x, this is a function of x. So the motivation to study this problem is that in nature, the bottom is not flat. So the bottom topography may be any kind of arbitrary shape near the coastal areas. So the study of the surface wave interaction with floating structures over arbitrary bottom is very important. And this bottom topography shape may be convex, concave, and any kind of trench topography or parabolic hump or type bottom topography. And the structure may be horizontal, vertical, it may be thin or it may be thick elastic structure, but for here, since we can model as a ice shelf already, like Professor Mellon and many others have discussed that ice shelf can be modeled as an elastic plate. So for this purpose, we have considered that if at the free surface, the elastic plate which is freely floating on the free surface, and if we have some kind of bottom topography which is arbitrary in shape, we have considered here kind of hump type bottom topography. So if we want to see the effect of this hump type bottom topography as well as this elastic plate, so now the mathematical question come, how to solve this mathematical problem. So in the literature, many authors have studied like boundary element method, finite element method to solve such kind of arbitrary shape bottom profile. But here I have used the semi-analytical method, which the step approximation method, in which we have approximated this bottom profile by using successive steps. So according to the successive steps, we have divided the whole domain into 2m+2 regions according to the depth of the water. And again, in each region, we have a governing equation. Since we are working in 3-dimensional, so the governing equation will be the Helmholtz equation and free surface condition, and these are the boundary conditions in respective regions. And another is that we have a elastic plate condition due to the elastic plate on free surface, and this D is the flexural rigidity here, and this epsilon is the thickness of the plate. But in this problem, we have considered the very thin structure. So in the mathematical numerical analysis, we have taken very a small length of the small thickness of the elastic plate. And since the plate is freely floating, so the shear force and the bending moment which will vanish at the plate edges, and it will be 0. So it is given by this expression. And to know the behavior of the reflected and transmitted wave, we have a far field condition which involve the reflection and transmission coefficients. And now we have applied the eigenfunction expansion method in each region, respective region from phi 1, phi j. This is the region above the hump topography, and in the plate covered region, we have a eigenfunction expansion where we have a plate mode which is n equals to -2 -1, and this is the non-propagating mode. These are the propagating mode due to the elastic plate and due to the free surface, and we have corresponding eigenfunction here. Now we have the dispersion relation due to the elastic plate on the free surface, which is given by this expression. So if we solve this expression, we will find out the roots of the equation, which is we have a complex conjugate roots and positive real roots corresponding to this dispersion relation. Now, since we are working in the continuum medium, so we have since virtual interfaces which we have created due to the variation of the depth. So due to the continuum medium, we have a continuity of the velocity as well as the pressure. So along each interfaces, we have these boundary conditions. Now, due to this virtual boundary condition, each interfaces, if we apply the eigenfunctions orthogonality relation, we will obtain a system of equation which has this size. Now, the system of equation which have m and n, m is the number of steps to approximate this bottom profile, and capital N, that is the numbers in the truncating series in this series. So now the further question come into the mind that how many m are required to approximate different kind of bottom topography. So for this purpose, we have taken a very simple case that if we consider this parabolic hump type bottom topography, and if we perform the convergence study, we have plotted reflection and transmission coefficient for various values of m and various values of wave numbers, and corresponding to each wave number, we find out that m equals to 240 steps are enough to achieve the good accuracy in reflection and transmission coefficient, that is up to 4 decimal accuracy. And this last column corresponding, it will shows the energy balance relation, which is obtained with the help of integral theorem, which is given by this expression, r square plus gamma t square equal to 1, where gamma is the coefficient which is given by this. Now, the free surface elevation is given by this relation. This is the free surface is associated by this velocity potential, and the deflection of the elastic plate is given by this, and the surface strain and shear force is obtained by this relation. Now, let me discuss the numerical results. We have non-dimensionalized the parameters and we have considered these values and find out that first we have performed that study for convergence of n, that is number of in the number of terms in the truncated infinite series. We have find out that n equals to 20 number of terms are enough to achieve good accuracy in result, that is up to 4 decimal places. So further, for the parabolic topography, we have considered m equals to 240 and capital N equals to 20 and solve the system of equation and find out the reflection and transmission coefficient. Now you can see that for validation purpose, we have taken two type of validation. First is, if we consider the bottom is flat bottom, that all the depth equal to 1, and the structure which is on the free surface, if it become rigid structure, in that case the flexural rigidity we have taken very high, that is 10 to the power 10, and the present problem will reduce this problem rigid of our flat bottom, which is solved by Lenton in 2001, and you can see the results are well matched with the result produced by Lenton. Now further what we did, we have taken the validation with wave scattering over arbitrary bottom topography. So in this case, there is no structure on the free surface, but we have taken this topography, which is given by this relation. Actually, this topography is considered by Porter and Porter, and in one of the paper by Tsai in 2018, and we find out that if we take the particular parameters, our result is well matched the result produced in the case of arbitrary bottom topography. Now, this is the energy balance relation already I discussed. You can see the value is approximated 1, so our result is well matched. Now, to see the effect of the parabolic bottom, you can see that here reflection and transmission coefficients are plotted versus wave number. And you can see in the flat bottom case, the reflection coefficient is given by this red line, and in parabolic case, this is dotted green line. So you can see if we have a parabolic hump type bottom topography, that can produce more reflection in comparative to the flat bottom. So the transmission of wave energy to the seashore side will be very less if we consider such kind of bottom topography. Now further, to see the effect of the length of the elastic plate, you can see that here reflection and transmission coefficients are plotted again versus wave number, and you can see if we are increasing the length of the elastic plate from 1.0 to 3.0 in the non-dimensionalizing form, and you can see the reflection coefficient is increasing and transmission coefficient is decreasing. But we are observing such patterns, such it is not uniformly increasing. This is due to the mutual interaction of the incident and reflected wave between the area of the hump as well as elastic plate region. And this is the effect of the gap which is between the hump type bottom topography as well as the elastic plate. And you can see if we are putting the structure that if the gap is more from 0.5 to 0.9, we have taken this value, and you can see in this case the reflection coefficient is more and transmission coefficient is less. And another effect of water depth. Similarly, you can see if we are decreasing the hump height, like if depth from 7.0 to 5.0, that means we are increasing the hump height and we are observing more reflection and less transmission. And this is the effect of angle of incidence. In this case, if we are taking the higher values of angle of incidence, in that case, the reflection will be more and transmission will be less. Now, the another parameter was involved, that is the plate deflection. So now you can see we have here plotted the plate deflection versus length, and you can see that if we are increasing the rigidity of the plate from 10 to 10 to the power 3, in that case plate will become more rigid, and you can see that the plate deflection here is less in case of the rigid plate, because plate will become more rigid and in that case it will be deflect less. And this is the angle of incidence on plate deflection, that higher the values of theta, we are observing less deflection, because more energy will be reflected back and less transmitted, so that we are observing less deflection. Similarly, the another parameter, that was the strain of the plate, you can see that if we are increasing the strain rigidity of the plate, in that case the plate become rigid and we are observing the less strain on the plate. And since we are considering the freely floating plate and at the edges we have a consider the shear force and bending moment is vanishing zero, so that's why we are observing zero strain. Similarly, the shear force, you can see for the higher values of rigidity, rigidity, we are getting the shear force which is very, very less as compared to the less rigidity of the plate. So let me conclude the topics. So we have considered the diffraction of water wave by an elastic plate over an arbitrary bottom topography. So we have solved this problem with the step approximation along with matched eigen extension method, and we have analyzed the effect of various system parameters on plate length, and as well as the another hydrodynamic quantities, that is the shear force, shear strain, and plate deflection. And this is my ongoing work. We have taken arbitrary shape of the elastic plate, and we are trying to approximate the plate thickness by the step approximation, and this is still ongoing work. And the present work is published in Archive of Applied Mathematics recently, and these are the few of the references which I have used in this work. So thank you very much. Thank you, the organizing team who gave me the opportunity to present these works. And thank you so much for your time and attention. So question, please. Thank you. Thank you so much.
Thank you very much indeed, Amandeep.
Thank you.
Does Ellie want to talk? Can you raise, sorry.
Yes.
Ellie, someone raise their hand and want to speak.
Yep.
Hi, can you hear me?
Ellie, could you go?
Yeah, I can hear you.
Yeah, could you go ahead and...
Great. I'll just start my camera in order for it to be a bit more human. Yeah, nice talk. Thank you very much for that. I was wondering if you ever tried to normalize the distance and the flexural rigidity by the incident wavelength rather than the thickness of the plate.
So sorry, can you repeat your question?
Yeah, no problem. I was wondering if you ever thought of normalizing the distance and the flexural rigidity by the incident wavelength rather than by the thickness, and also what would be the consequence of doing such a normalization.
Actually, what we are doing, we are seeing the effect on the reflection and transmission coefficient for the variation of flexural rigidity as well as the gap between the structure. So I have observed that if we are increasing the gap between the structure and hump, in that case, the reflection will be less. and transmission will be more because there is more distance between the structure as well as hump, so more energy will be transmitted. So the thickness effect I have not considered here, but my observation is maybe that if we consider the thickness, the higher the thickness, maybe produce more reflection and less transmission.
Okay, but if we go back to the next slide you have,
This one?
maybe the next one, sorry, when you have D over, yeah, this one. So you have
Yes.
D over H to the fourth, and I was wondering, there might be a wavelength in your problem, right?
Yes.
Like an incident wavelength. And I was
Yes.
wondering if like normalizing the flexural rigidity by the incident wavelength, lambda, at the fourth.
No, this is I'm normalizing this flexural rigidity by the depth parameter. H1 is the depth in the first region initially.
Yeah. Okay, but I guess my question is why the depth and why not another value?
We can take a like a normalized wavelength also. We can normalize in d by lambda, like lambda by 4. But in that case also I'm observing the same pattern, that if we are increasing the flexural rigidity, in that case also plate will be less deflect. Actually, in this analysis we have taken the depth normalization, but I can also consider that wavelength for the non-dimensional. Yes, I have not plotted that one here.
Great. Well, thank you very much.
May I ask you a question?
Sure, sure.
Right. Maybe I missed, I'm sorry. How many evanescent modes you took into account at each step?
Yes. Yes. Can you repeat your question, sir? In each step?
At each step, there are a number of evanescent modes, right?
Yes, yes.
How many modes you took into account?
Actually, in that case, we have taken here the evanescent mode in each region, this one.
Mm-hmm. So number of modes, formally speaking, is infinite. But in your calculations, apparently it was a finite number of evanescent modes, right?
Yes, I'm taking the finite number of ones.
How many?
Actually, for this analysis, we have taken n equals to 20 modes. This one.
20 modes?
Like
okay, yeah. Did you find a convergence of your results when you increase the number of modes?
Yes.
Right?
Yes.
Okay. Okay, thank you. Yeah, this was my question.
Yeah, actually, first we have taken one number of evanescent mode. If we are increasing the number of evanescent mode, we are getting this analysis, and we are observing that n equals to 20, 25, and further so on. We are getting the reflection and transmission accuracy up to 4 digital place, but there is no more variation after that.
Okay, thank you.
Thank you.
Okay, thank you very much again, Amandeep. And just remains for me to say we reconvene at 1:35 back here. Thank you all online and all in the audience for asking such great questions and being for such great audience. And just remains to say thank you for all 4 speakers for giving such great talks. Thank you very much.